to click that one.
Hey there, folks. It's Rick Uzzi here with Pete Olivia, and today we're going to be talking about OFDM, DOCSIS 3.1. We'll be right back. Thanks for joining us again. Rick Uzzi here with Pete Olivia from Zcorum. And Pete, last week we said we were going to talk about OFDM and TrueVision. And that's interesting. Yeah, let's just stop that. Okay. Yeah, let's just close the whole thing. Oh, that reminds me, we had some technical difficulties last week.
We're having new technical difficulties.
Yeah, you'll notice my mic is today fully plugged in, so we didn't have any last minute craziness going on trying to get the connection working, but we are working today. But that was interesting. I've not had that happen before. I've tried something.
Well, it was streaming our stream.
It was streaming the stream, so we would have had a really bad echo.
That would have been a great little loop, right?
Yeah.
Infinite loop there.
So anyway, last week I thought we were going to be talking about TrueVision and OFDM today, but you thought you were going to be out of town, and then that changed at the last minute. So I had set up just something on OFDM in general. I think that'll be a good lead-in to next week. So next week we're going to talk about OFDM and TrueVision, and you can see some of the TrueVision tab and some of the features with OFDM and TrueVision. But today we're just going to be talking about TrueVision in general. If you would like to chat with us, go ahead and chat with us. I was going to try to see if I could see the chats while we were actually demonstrating, going through the slides, but that's the problem I just had a minute ago.
It started streaming on our stream.
Exactly. So we will go ahead and just look at the end and see if you have any questions, and we'll take those at the end. So anyway, OFDM, let's talk about what that is. First, we're going to start basically with just DOCSIS and kind of how it's evolved over time. So DOCSIS 1.0 came out in 1997, and before that it was kind of the Wild West with cable modems. You had to have cable modems from the manufacturer of the CMTS or it didn't work. There was no interoperability. And can you imagine that, how bad that was at that time?
It's kind of like some of the old fiber stuff in the recent past.
Yeah, maybe DSL and stuff where there were no standards. So DOCSIS was great. It made manufacturers get on the same page as far as these standards. So again, DOCSIS 1.0 in 1997, and then pretty quickly it moved through 1.1. They made different changes. I think in 1.1 they added the 8 equalizers for proactive net. Well, actually at that time it wasn't proactive network maintenance. It was just 8 equalizers to overcome impairments in the plant. And DOCSIS 2.0, I think that's when it went up to 24, and some other changes, some increases in the upstream that happened in 2.0. So all that happened pretty quickly. And then in 2006, DOCSIS 3.0 came out, and that's when they started doing channel bonding.
Yeah, you got all the bonding.
Yeah. And then there was this long time gap between 3.0 and 3.1, and there was a pretty significant change in 3.1, and a lot of people thought it should be really 4.0 because it was such a significant change. It was a long period of time.
Well, that's coming. 4.0's coming.
4.0's coming, yeah. And it may not be that different from 3.1, but between 3.0 and 3.1, it was a major change. So, just in general, really nothing's changed in how TV's done. It has been done since analog broadcast TV. It's been, 6 megahertz channels, or 8 megahertz, I think, if you're in Europe. And that went for analog broadcast TV, analog cable, digital cable, up until now, I say 3.1. So it's been done this way, and you had these 6 megahertz channels, and you've got these guard bands on each side.
Yeah, so they don't overlap.
They don't overlap. Mm-hmm. So that's how it worked. Is you have to separate these channels, and you've got these guard bands on the side, and that way you can send separate signals down different frequencies on there, and that's how you've got your cable TV channels that you tune to. That's how it's been done, and it worked really well. And then, as I mentioned, when DOCSIS 3.0 came out, they added channel bonding.
Right.
So you can bond, I guess, multiple upstreams and downstreams.
Yeah, so that you could, in other words, instead of just one channel, you can have a couple channels and hop across.
Yeah, and the reason this was done was for more throughput. So you can have, you could bond up to 16 or 32 downstream channels, and then you've got a lot more throughput that you can send down to that subscriber. So that was great. So why go to 3.1? Well, it's the same thing. We want more speed, and I think, again, 3.1 came out, 2013, but it probably is just, it wasn't implemented for several years. I think there's equipment changes. It was a big change. So they were thinking far ahead on this, because really what they were thinking was, we're going to have to compete with fiber. So they were looking at how they could compete with fiber, and one of the problems with bonding channels, you lose some spectrum, I guess, the more channels you bond, because you've got your guard bands.
Well, you know, there's just ways to capture spectral efficiency and things like that, that they picked up in 3.1.
Right.
It's made better use. You're always trying to get more with the same amount, right? It's like anything else.
Yeah.
In computing, it's the same type of thing. Anyone that keeps an IT budget knows it's always like, okay, I want you to do more, and I'm cutting it.
Right.
So that's just the way it goes.
So, you know, if you're going to bond all these channels together, for each one that you bond, you're losing a little bit of spectrum on those guard bands. And that's where 3.1 came in. And now what they have is what's called an OFDM channel. That's Orthogonal Frequency Division Multiplexing, OFDM. And now you can have channels that can go from 24 megahertz wide to 192 megahertz wide. And instead of with DOCSIS, as it is today, DOCSIS, you know, from when it started, 64 QAM and 256 QAM, now you're talking about up to 4K QAM, or 4096 QAM.
And in theory, eventually 16,384. So
right.
16K QAM eventually. So.
Yeah, 16K. And actually, it's required up to 4K, and then optionally, equipment manufacturers can do up to 16K QAM. So.
Yeah, those constellations. It's going to look like a
square.
Yeah. It's
a solid square.
Paint the square.
Yeah. So, and the 24 and 192 is interesting, because if you'll notice, those two numbers are divisible by both 6 and by 8. So again, here in North America, we've got 6 megahertz wide channels, and then in Europe, they've got 8 megahertz wide channels. So because of that, and they're both divisible by those numbers, 24 and 192, then you don't need separate specs, DOCSIS 3.1 specs for North America and for Europe. So that's the reason that they did that. So OFDM, again, think of it like one big channel. And then you might be thinking, well, that's, you know, how does that one big channel work? Well, that's what the orthogonal part does. As far as the frequency division multiplexing, or FDM, that's actually something that's not new. That's part of QAM, or part of the technology right now. All that means is that you're dividing the signal up among channels. It's the orthogonal part that's new. And actually, that's just new for cable.
And I mean, it is one big channel, but there are like thousands of subcarriers in there, depending on your spacing. It could be either roughly 4,000 or 8,000 little sub-slices.
And
depends on how you set it up.
Yeah, and so again, the orthogonal part is different, and new, but it's new for cable. It's actually, the OFDM part's been done with Wi-Fi, wireless, and even DSL.
Yeah, it's been around for a while, definitely in cellular. Yeah, you're seeing it in Wi-Fi too.
Yeah, so it's new for cable.
Satellite.
And something else, you know, as you look at this channel, something that you need to keep in mind is that there's a PHY link channel, or a PLC, and this, I believe, this is what keeps the modems, tells the modem, the physical plant, you know, what upstream frequency it's on, and
basically gives it a lay of the land. Like, you know, here's where, you know, the OFDM info. It's basically like the blueprint of the channel. Tells it what it is, how wide it is, all that stuff.
Yeah,
right?
how wide it is. Yeah,
it's all the information on the OFDM channel.
Yeah, and the nice thing about this is you can put this PHY, or this PLC, or this PHY link channel wherever you want. It's 400 kilohertz wide. It just needs to be in a 6 megahertz band, and then right in the center of that band. And then it can't have any exclusions. And that's something else that's different with OFDM, is you can have these exclusion areas.
Yeah, because there is some overlap with LTE. Actually, as they expand it out, there's going to be more.
Yeah.
But yeah, the PLC, you want it to be somewhere where, if the modem can't find and talk to the PLC cleanly, you're not going to do anything with OFDM. So you want it to be somewhere where there isn't.
It's really clean.
Yeah, real clean. No errors. No interference. Good SNR is great. You know, things like that. If you have problems on your PLC, it'll never lock on and find anything. It'll be toast.
So again, OFDM allows you to have these exclusion bands, and here's an example where you might have LTE interference, and you can actually turn off the subcarriers in that area, and that way you don't need to worry about that interference. Another thing you can do with it, if you've got legacy channels, legacy single carrier QAM kind of channels, then you can actually even put those in an exclusion band. So you can have OFDM, one big OFDM channel, but you can have an exclusion area where you've got some other.
Yeah, and if you got pockets that you know are just horrible, for whatever reason, you could just exclude them.
You could fix them, or you could exclude them.
Yeah.
Yeah. And then something else that's part of the OFDM signal are these continuous pilot signals, and these are really what kind of keep everything in track. And I swear I missed my. Let me go back and see if I.
Your OFDM, your little orthogonal.
Yeah,
graph.
It must be after this. Okay. Or maybe I just completed.
Because you said you were getting all orthogonal. I was like, okay,
I
know which graph you're coming with next.
Okay, I'll talk about orthogonal in a minute. Yeah. And if it's not here, I'll have to explain it. That will be hard. These continuous pilot signals, what they do is these are spaced evenly throughout this OFDM channel, and that helps determine the frequency and the phase tracking for the cable modem, keeps everything kind of in place, helps it keep the orthogonality, which we'll talk about, I hope.
And it also, that's how it finds the PLC too, because those continuous pilots have a little bit more bump above the rest of the signal, and it sees, it hits those pilots coming in. It's kind of like, I guess as it's coming into the runway to land, it sees the lines on the runway and knows where to go. I guess when they land planes, I don't fly, but I hope. But it's a way to guide the device to find out where it is.
Right. So, yeah. So you've got these pilots, and these pilots are 6 dB bumped up from the signal as you go. And so if you were looking at your OFDM signal on a spectrum analyzer, you actually see these little 6 decibel spikes kind of evenly spaced throughout that. And then they've also got these scattered pilot signals, and what these do, these scattered pilot signals are for proactive network maintenance and your adaptive equalization. So this is something that these pilots actually show up at various places in the OFDM channel, and they will eventually visit every single one of these subcarriers to try to figure out how things are going.
It helps the device kind of get a feel for where the problems and whatnot in the signal, so it can communicate back to CMTS and adjust. And it's basically it's its own little diagnostic, right? To know where the good, bad, and different points are on the OFDM carrier. So
this may, add in the wrong spot. Okay, so all right, so this is how all this works. So basically, when you're looking at this big OFDM channel, within that you've got all of these subcarriers, and again, you can have up to 7,600 of these subcarriers going through here, and they actually overlap, which is kind of odd as you think about it, because you'd think these would be interfering with each other, but they don't because of this orthogonal property to them. And what does that mean? Orthogonal means it's like a 90-degree or perpendicular.
Yeah.
And it's actually the same term that they use in astronomy. I don't know if you know this, but in astronomy, when you're looking at two bodies in relation to yourself, if they're at right angles, that's called orthogonal. So that's where that term comes from.
Yeah, and this is how you eliminate all the lost spectrum, because you don't have guard bands.
Right.
Really what's going on, if you look at a graph like this red one, when he hits 0, the next one black is actually, I guess at 1, if you're thinking sine or cosine wave. So they're actually overlapping, but where one signal's bottom, the other one's peaked.
Right.
So they can overlap, and you don't need all these guard bands that you would have in a traditional SC QAMs.
Right. So if you look at the two kind of center ones there, almost in the center, you see that line coming down. So what Pete's describing there is you've got your peak on one signal, and then as you trace that down, it's hitting the null of all the other signals. So you have no interference, and you've got all of these little subcarriers overlapping each other.
Yeah.
And something interesting is that QAM itself is kind of orthogonal. It is, because quadrature also means right angle or 90 degrees. And what you're doing in QAM is you're sending a signal down, but then you're modulating it. And that's what QAM. So you've got quadrature modulation.
I think you're going to make
amplitude. Quadrature amplitude modulation. Yes, QAM. Okay, so the so the quadrature
tongue
part.
Twister. Say it 20 times.
Yeah, the quadrature part is, again, you're sending this signal down, but you're modulating it first into 2 signals, and you're modulating in such a way that they are at one is in phase, and the other one is 90 degrees out of phase with that, and that way they don't interfere. So when you're talking about OFDM, you've got all of these little mini QAM signals that are already modulated in a sense at right angles, and then you're doing this orthogonal piece here, so they're not interfering either. So it's very interesting. Again, the subcarrier spacing is either 25 megahertz or 50 megahertz.
Yeah, depending on and then that affects how many subcarriers you have, right?
Yeah, right.
So I mean, there's a lot of advantages to that because your error correction, because you got a smaller span, you can, it's easier to do error correction on those. They also do some interleaving of time division interleaving and frequency division and interleaving, where they send different bits of the same code depending on how your settings are set up, in case you get interference. If you've got ingress bursts or whatever, and they send pieces of it, there's some over a little bit over time and across different frequencies, so that it doesn't crash. In a SC-QAM, you get a time slice and you're on this frequency, right? With OFDM, when it actually sends it, it sends pieces of the code word actually across subcarriers at different frequencies in there, as well as time. So if you've got some interference somewhere, it's not completely wiped out because it's not all in one place, right? The actual code word comes across time and frequency. So they did a lot of things like that. The low density parity check is I don't know. They're probably stealing some of your future stuff.
No, I don't have anything. No, I'm not talking about that. So that's a good point. So in DOCSIS 3.0 and before, you had Reed-Solomon for your forward error correction, but they've got now LDPC.
Low density parity check. I don't know why I can remember that, and I can never get the letters right.
Yeah.
But yeah, well, you had all the history on that. Come on.
No. I just know. Well, I was telling him it's interesting that as I was looking at this, that actually came out. The guy Gallagher. He told me his name. He remembered his name.
63, I think.
Yeah, it was early 60s. So he came out with this method for error correction called low density parity check, and it's very complicated. Very complicated. It works really well, but it's very complicated. So complicated that they didn't even have the computing power at the time to be able to make it work. So.
It just wasn't functional because they didn't have the Moore's law hadn't kicked in enough, right? Moore's law.
Yeah.
We were joking about all the names you got to remember from Shannon, Moore.
Moore's is the one where computer power doubles every so often.
Yeah, I think it's like it. Yeah. There you go. Was it 18 months?
Something like that. Yeah.
See, I told you there's smarter guys than me out there. They'll never be an Olivia principal. So, but yeah, and what happened was they kind of forgot about some of that, and then I think it was in the 90s, early 90s, that it kind of resurfaced and started playing with it. And when they started checking it against other error correction methodologies, the old the turbo codes or whatever they call them, and it was actually doing better. So then a lot of these, that's why some of these technologies you're talking about have adopted OFDM and low density parity check and all that is included in there because it's more effective. And with the new computing power nowadays, even a small modem, I guess, now has the power to do what they couldn't do in the 60s, right?
Yeah. So OFDM is on the downstream side, and then on the upstream side, we've got OFDMA, which is orthogonal.
You got it. Frequency division multiplexing access.
Multiple access instead of multiplex.
Multiple access. Yeah. See, I told you all. It's so much easier to say OFDMA there.
It is.
I don't know why.
Yeah. So,
but that's the upstream side. Yeah, and there's differences there too.
A few differences. Yeah. So you still have the subcarriers. You've still got pilots in there a little differently in how they're handled.
I don't know the way it accesses things and time slices and things like that. So.
But something interesting about OFDM, if you're going to roll this out, is you don't need to do it all at once. You can have your DOCSIS plant the way it is today, as long as you've got the frequency to spare. Up to if you got 192 megahertz or something in between that 24 and that 192, you can set up an OFDM channel, and you can have your standard carriers in other places.
There's a lot of that shifting going on. People, freeing up QAM space to put it in. And we actually do have affiliates that they'll have their traditional SC QAMs, and like 3.0, you can bond in the OFDM channel. I actually have some that do like 32 SC QAMs and an OFDM channel. A tremendous amount of downstream bandwidth that you can get out of that. But like you said, that's a good way to segue in. And then once you get everybody on OFDM, then you can free up the old SC QAMs and then maybe put in OFDMA. We actually have affiliates that have both, that have OFDMA and OFDM.
Yeah, that's a good point, because you could start with OFDM and you don't have to implement or deploy OFDMA right away, just like a lot of operators started with maybe bonding just on the downstream and then later added some bonding.
Yeah, most of the draws on the downstream side to start with. But like I said, there's a lot of advantages to doing that. There's spectral efficiency. One of the interesting things about OFDM versus it's kind of, it can you can have multiple profiles. That's something that we didn't cover here. So maybe we'll get into that next week, what to look for.
Well, no, that brings up a good point, because something with what he's talking about is, on DOCSIS 3.0 and lower, if you had a customer or an area, let's say, of your plant where you could only do QAM 64, then basically for everybody there you had to do QAM 64.
Yeah, well, it's just if your spectrum is, if you don't have enough quality space to run signal, whatever QAM modulation is on that frequency, that's just what it is. It is what it is.
It's your it's your lowest common denominator that you have to do. Yeah.
And in an OFDM world, you can actually determine. You can find that's ideally what you want to do is find the. This is what I was talking to Karthik at CableLabs about. I'm really dorking out. You can go and find places in your OFDM spectrum that are really good, and maybe put the higher order profile. So the way it works is you have a base profile, profile A, that every device that's going to do OFDM has to lock onto. And that's ironically for a lot of folks 256, right? Which is like max in the 3.0 world. Right. But some will make 256 their base profile for the OFDM channel, and then have 512, 1024, 4096 for B, C, and D. Or I've even seen somebody do it differently, where like B was really high at it. That was unusual. But usually, as you go up the chain, 0, 1, 2, 3, A, B, C, D, they're going to run out of letters at some point when they get enough capability to do profiles. They only can do 16 right now, but it's going to expand over time. But those different profiles have different modulation orders. And what happens is you define where in your OFDM channel which subcarriers, each little slice that can do those higher order modulations, right? And a device can lock on, and that's where the next code word pointer comes in. That's when the CMTS says, hey, you expect those are where your code words are going to be, and it's at this profile level because of your capability. So the advantage of that is for the same span, you can have a higher order modulation. You can get a 4096 QAM versus say 256, where it's in the SC QAM world, it was just flat. Whatever it was on that, if it was 64 QAM, then everybody that uses that channel 64 QAM period across the whole 6 megahertz. In the OFDM world, because they're all sliced into little, 50 kilohertz, 25 kilohertz subcarriers, each of those can be assigned different profiles, right? And you can transmit, the same device can transmit and adjust profiles based on plant conditions. Right. So it could be that part of the day it might be really sunny and you're having expansion or rain or something like that. It might affect the plant. The plant can adjust and tell the device to use different profiles. And then you could get the same, you can get more throughput in the same spectrum. Does that make sense? I don't know, am I dead dork out there? Does that make sense?
Probably makes sense to some of the people watching. To me, it was like, okay. No, some of that makes sense. So again, very flexible. So OFDM, there's a lot you can do with it. Again, you've got the exclusion zones, bands. You've got the different kinds of modulation that you can do. Also, one of the things that was new in the 3.1 spec was they actually included proactive network maintenance. So even though we've been doing PNM using these adaptive equalizers and other things, now they've actually included some things in the spec. So with proactive network maintenance, you're going to be seeing changes as well on some things that you can do. I don't know if you know about any of that.
I'm involved in it, but probably conversation for other.
Yeah, maybe another
PNM,
day.
Another PNM discussion.
Yeah. So anyway, I don't know. Let's see if we have any questions here. Nobody has any questions. So
I wonder if our chat window is broken.
It's probably broken. You may be chatting and we may not be seeing it.
Well, I guess you can't go look because it's going to fire up your video, right?
Yeah, let's see. It'll fire. Yeah, so let's see, can I see it right here? No, anyway. So if you're chatting with us, my apologies. Let's see if I got anything in here. It should be there. Anyway, so if there's
anything else that we can cover, profiles we covered. We talked about the PLC. We kind of mentioned next code word pointer. We talked about the various profiles. I talked about spacing. You talked about ability to exclude or for the channel to adjust by itself. Better spectral efficiency based on your MER. You can get higher order modulation. So trying to think if there's anything we missed.
I think that's the basics, and really that's what that was my point today, was so that next week when we show you the TrueVision OFDM tab, you'll kind of have an understanding of what OFDM is and kind of some of the things that we're looking at. For example, when we look at a PLC in there, what does that mean?
Yeah, what does that mean?
Yeah, so again, if you were, I didn't see any questions or chats in there. So, but if you were trying and I just can't see it because we're broken on this side, if you've got a question or something like that, just go ahead and leave it on the recorded video, which will be up immediately after this live broadcast. In fact, you may be watching the recorder right now. If you have any questions, you can just type it in there, and we'll be notified with that. And I will send that to Pete.
I was going to say, ask Rick all the questions.
So he can answer those, or whatever other expert I can find. But you said you talked to all the guys at CableLabs, and actually you were in the CableLabs group, some
Genius,
group.
yeah. I'm involved in a lot of those P&M and Genius and things like that. Yeah.
Yep. So next week, again, what we'll be talking about is we'll be going back into TrueVision next week. We took a break this week to talk a little bit about OFDM, but we're going to go back in and show the OFDM tab in TrueVision and how we can take some of the diagnostics information.
Basic things you should be looking for to troubleshoot, right?
Yeah.
And how you can find it, use TrueVision to find that without having to drive out and go to the house. So
yeah. Okay. So that'll be next week, the OFDM and tab in TrueVision. We'll see you then Tuesday at 3 o'clock. Take care. Bye-bye.